Alright, I'm going to be doing problem number 6, which states y triple prime minus y prime is cosecant of t. The first thing, or sorry, with the bound of negative pi over 2, t is included up to pi over 2. And then, let's see. The first thing I did was find our homogeneous solution, or I guess characteristic equation in terms of r. So this one's pretty easy. I just substituted r for y prime. So r cubed minus r is cosecant of t. And since we want to find the roots, or I guess when it's equal to 0, I think it was pretty simple to distribute the r. So I got r times r squared minus 1. And then when r is 0, r is 1, or negative 1, we get 0. So we can use the form c1 e to the rt, c2 e to the rt, and etc. And then all I really did was I used our roots right here, and then I plugged it in. So c1 is just 0, because e to the 0 is just 1, plus c2 e to the 1t, c3 e to the negative 1t. And then this also gives us our y values of y1, y2, and y3. The next step is to find the particular solution, which is over here. We have the first part, which is the homogeneous, or I guess the character with the comparable solution. So all we have to do now is find the particular solution. So basically what we do now is we find the Wronskian for each using the formula u of 1. The u of 1 is part of this. We already have the y component. So u of 1 is the Wronskian for each matrix over the main Wronskian. So all I did was this column is y1 and this one is y2. Or sorry, this one is y1, this one is y2. Each is a derivative. So this is going to be y prime, and then y double prime. This is why it's all the same, because the derivative of e to the t is the same. For this one, e to the negative t changes as you derive it. And then one trick, or I guess the way I did it was, since this is a third order, basically that means cosecant of t is when y triple prime, so that means we can use a matrix, a 3x1. I guess it's y prime, y double prime, and y triple prime. It's 0, 0, and cosecant. So all I really did was I replaced this row for each. Started with row 1. I replaced the 1, 0, 0 with the 0, 0 cosine, or sorry, cosecant. And then I found, I multiplied the cosecant by the determinant for each. So this one was the negative 2 cosecant of t. Plug that back into the formula right here. And then that's negative 2 cosecant of t over 2 dt. Same thing for this one. I replaced the second row with this one right here with our cosecant matrix, or column, I guess. And then I did the same thing. Found the determinant of the 4 right here, the bottom 4. And then I got e to the negative t cosecant. And then I found the integral of that w2, which is this, over w, which is 2. And I did that for the third one over here. But this time I replaced the third row with 0, 0 cosecant. And then I multiplied that by the determinant, which is just e to the t, over the w1, sorry, the w, which is 2. So 1/2 integral of e to the negative t cosecant t dt. And then so this is all going to be u1, u2, and u3. And all we do is we plug them back in to our top formula right here, the particular solution. And then since we already have y1, which is just e to the t, or sorry, y1 is just 1, because there's nothing of in front of c1. y2 is e to the t, and y3 is e to the negative t. And then we use that same thing, we just plug it in here, multiply it with the with each of u1, u2, and u3 that we found down here. And this is our solution. C1 plus C of 2 e to the t plus C3 e to negative t. I believe it's not supposed to here. Minus integral of cosecant t dt plus e to the t over 2 times integral of e to the negative t cosecant dt plus e to the negative t over 2 times the integral of e to the t cosecant t dt. That is my work for problem number 6.